Okay, today we're going to talk a little bit about multiplying and dividing radicals. Now, I mentioned a little bit about this in the last set, um, so I'll probably start with what I mentioned last time. In that, in order to combine radicals through multiplication or division, they need to have the same index. But once they have the same index, it's actually a bit easier than working with addition or subtraction. Because if your two or more radicals have the same index, you do just multiply the radicands together. And I'll jump right into a few examples of working with this. This is example 1 off of page 284. And we're asked to multiply and simplify the following. Negative 3 root 2x times 4 root 6. We are also told that x is greater than or equal to 0 in this example, and that is just to meet the requirement that we're not taking the square root of a negative number. Okay, so multiplying these across. Now, the order of multiplication does not matter. I wouldn't expect everybody to write this out each time, but this would be the exact same as if I were multiplying this. These two are the same, so let me just multiply the parts. Negative 3 times 4. That's negative 12. Root 2x times root 6 would just end up being root 12x. I just multiply the radicands together, and that's it. So as long as my indices are the same, then I just multiply the radicands together. This would reduce because square root of 12 is the same as the square root of 2 times 6, which is 2 times 3. And since the 2's show up twice, I could bring those out once and end up with negative 24 times root 3x, not root 33. That doesn't help me any. Negative 24 root 3x. Moving on, in B, we're asked to multiply 7 root 3 by 5 root 5 minus 6 root 3. Now, my normal algebra operations and order of operations still holds. So if I'm multiplying everything in this set of brackets by 7 root 3, what's going to come out of that? I'm going to end up with 7 root 3 times 5 root 5. 7 times 5 is 35. Root 3 times root 5 is root 15. I'm going to minus 7 root 3 times 6 root 3. 7 times 6 is 42. Root 3 times root 3 is root 9, but that actually simplifies quite nicely. I can't do anything with the 35 root 15. That's pretty well done. But the square root of 9 is just 3. So I end up with 3 times 42, or 126. And that's about as far as I can take that. Part C of that example. I'll give myself a little more room for this one. 8 root 2 minus 5 times 9 root 5 plus 6 root 10. There's radicals involved, but it's pretty well one binomial multiplied by another. So I need to make sure I get all the cross terms. 8 root 2 times 9 root 5. 8 times 9 is 72. Root 2 times root 5 is root 10. 8 root 2 times 6 root 10. 8 times 6 is 48. Root 2 times root 10 is root 20. Negative 5 times 9 root 5 is negative 45 root 5. And negative 5 times 6 root 10 is negative 30 root 10. A couple of things I can do. I can combine the like terms. 70 root 10 minus 30 root 10, I should say the like radicals, would be 42 root 10. 48 root 20 would be 48 times the square root of 2 times 10, which is 2 times 5. Can't do anything immediately with the 45 root 5. However, this will simplify. Since there's two 2's inside, I can bring one out. 96 root 5 minus 45 root 5, and then I end up with two more like radicals here on the end. So I can combine those, and I end up with 42 root 10 plus 51 root 5. And lastly, just for kicks, 9 times the cube root of 2w, all multiplied by the cube root of 4w, plus 7 times the cube root of 28. Now my indices again match up, so I can multiply the radicands together. So for my first multiplication, I have 9 times the cube root of 2w times 4w, or 8w squared. For my second multiplication, 9 times 7 is 63. It would be 63 times the cube root of 2w times 28, or 56w. Then I look to simplify. The w squared I can't do anything with, but the 8 is 2 cubed. So I can bring a 2 out from that. I get 18 times the cube root of w squared. Plus 63 times the cube root of, and if I break 56 down into its prime factors, 56 is 2 times 28, which is 2 times 14, which is 2 times 7, and the w is still in the end. I've got 3 2's, so I can bring one out, and I end up with 18 times the cube root of w squared, plus, bringing a 2 out, 126 times the cube root of 7w. And I end up there. So, that's some multiplication. As long as you've got the same index, you simply multiply the radicands together. And then simplify as we talked about before. Another example ties into a bit more of a word problem. This is example 2 off of page 285. And in this case, we are given a diagram to work with. I won't go through all of the description of where this diagram comes from, but we are given a square with an equilateral triangle inscribed inside. That's some triangle I got going on there. And we are told, so these sides are all the same length, which means, of course, that these sides are all the same length as well. I apologize that my diagram is not perfectly to scale. The area of the square is 32 square centimeters. Then we're asked to find a few things. Find the perimeter of the triangle. Okay, so if I've got a square and I know its area is 32 square centimeters, and the area of a square, I should say, if one side is x, the area is equal to x squared. So x squared equals 32. So x is the square root of 32. Now, typically that should be plus or minus the square root of 32, but you really shouldn't have a negative side length. That tends to break the universe. And I can simplify that a little bit, because 32, wow, is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So x would also be 4 root 2. Now x is also one side of my equilateral triangle. So if x is 4 root 2 centimeters, then the triangle has a perimeter of 3 times 4 root 2, or 12 root 2 centimeters. These are again in exact values. I should say that we weren't just told to find the perimeter of the triangle, we were told to find the exact perimeter of the triangle. And that means if there's roots involved, we leave them as roots. Don't approximate with our calculators. Part B asks for the exact height of the triangle. So if I make my diagram again, only now I break this up a bit. This height h is what I want. One side of this triangle is 4 root 2, but that means that half of this side is 2 root 2. And then I can just go through Pythagoras' theorem. Know that one leg squared plus the other leg squared equals the hypotenuse squared. So then I ask myself, what's 2 root 2 squared? Well, 2 squared is 4. Root 2 squared is 2, so this works out to 8. Similarly, 4 squared is 16. Root 2 squared is 2. And 2 times 16 is 32. So h squared equals 24. So h equals root 24. Again, technically that should be plus or minus root 24, but the negative again, it would be unphysical. And we can simplify that because 24 is 2 times 12, which is 2 times 6, which is 2 times 3. With the two 2's involved, I can say that h equals 2 root 6, or the height of the triangle is 2 root 6 centimeters. And lastly, we are asked for the exact area of the triangle. Well, at this point that's not too bad, because I know that the base is 4 root 2, the height is 2 root 6, and the area of a triangle is 1/2 base times the height, or 1/2 of 4 root 2 times 2 root 6, or 1/2 of 4 times 2 is 8, and root 2 times root 6 is root 12. Now 1/2 times 8 times 12, or root 12, would be the same as 4 times the square root of 12. 12 is the same as 2 times 2 times 3. So this is the same as 8 root 3. And I would say the area of the triangle is 8 root 3 square centimeters. Alright, now to this point we've talked about some multiplication, but now we need to talk a little bit about division. And the same rule holds. I need to have the same index, but we get a little bit more complicated in the simplification of things. When you are dividing radicals, my wording. When you're dividing radicals and end up with a radical in the denominator, we try to remove the radical from the denominator. In a process we call rationalizing the denominator. And this can take a couple of different forms. Let's say I've got a over root b. I don't want that root b there. But conveniently, thanks to our work with algebra, I can multiply this fraction by anything I want as long as it equals 1. Meaning I could multiply it by root b over root b. In my numerator, I end up with a root b. In my denominator, root b times root b is the same as root b squared. And the square root of b squared is simply b. And now I have rationalized the denominator. I've gotten rid of the radical that was in the denominator before. Now, where it gets a little bit more complicated is when your denominator has something like this in it. Now what we do in this case is do something we call multiplying by the conjugate. What your conjugate is simply the same thing as your denominator, but with the sign reversed. And we would say that b plus root c and b minus root c are conjugates of each other. And really all that means is I've changed the sign of the term connecting them. Instead of b plus root c, I have b minus root c. Had I started here with b minus root c, I'd multiply by b plus root c over b plus root c. So why do we do that? If I multiply across the numerator, I'd get ab minus a root c. When I multiply across the denominator, b times b is b squared. B times negative root c is negative b root c. Root c times b is positive b root c. And then root c times negative root c is simply negative c. What's happened here, you'll notice that our cross terms cancel each other out. And I end up with ab minus a root c over b squared minus c. I've gotten rid of radicals in my denominator. Typically, if you're asked to rationalize the denominator, or if you're stating a radical in simplest form, you don't have square roots in the denominator, you might have to do something like this to get rid of any square roots in the denominator. And we'll look at a few examples of working with that. This is example 3 on page 287. And you're asked to simplify the following expressions. In A, you're simplifying root 24x squared over root 3x. Now again, since my indices are the same, I can simply divide the radicands. And since this works out nicely, 24 divided by 3 is 8, x squared divided by x is x, and this just becomes root 8x. But I can simplify the 8 part of this, and it would be 2 times root 2x. Alright, fairly straightforward at that point. Now in B, we've got a little bit more work in front of us, because we're simplifying 4 times root 5n over 3 root 2. Now there's nothing nice to divide here, so I can't just do a division and simplify from there, but I can rationalize the denominator. I'll multiply that by root 2 over root 2, and I would end up with 4 times root 10n. Root 2 times root 2 is 2, times the 3 is 6. The 4 divided by 3 would simplify, and I'd end up with 2 root 10n over 3. In part C, we're asked to simplify 11 over root 5 plus 7, and this is this case of a binomial with a radical in the denominator. So I'm going to multiply by the conjugate, and the conjugate of that would be root 5 minus 7 over root 5 minus 7. My numerator becomes 11 root 5 minus 77. My denominator, if I think here to what I end up with, I end up with the first term squared minus the second term squared. What will that be in this case? Root 5 times root 5 is 5, and 7 times 7 is 49. And so that's going to be the same as 11 root 5 minus 77, and 5 minus 49 is negative 42. 44. And you might notice that an 11 would divide out of all these things nicely. So if I divide by a negative 11, this would simplify to negative root 5 plus 7 over 4. And that's about as simple as I can make that. The last part of that example, D, I have 4 root 11 over y times the cube root of 6. Now, this one is a little trickier because I am trying to get rid of a cube root that's in the denominator. Now, bear with me on this one. In order to get rid of that cube root, I'm going to have to multiply by the cube root of 6 twice. Now what will I end up with in my denominator? Cube root of 6 times the cube root of 6 times the cube root of 6, which will be 6. Overall, I end up with 4 root 11 times the cube root of 6 squared. I can't combine these because they have different indices. And 6y on the bottom. Once again, that 4 over 6 would simplify, and I end up with 2 times root 11 times the cube root of 6 squared over 3y. Right, there are a few different examples of multiplying and dividing radicals. There'll be a few questions on the Google Classroom site. Thanks for watching.